Hello there. This is a video on chapter 7 on identities and solving trigonometric equations. So let us get started. I hope you're doing fine. So let me start by going over this PowerPoint here. Okay, so this is chapter 7, and in other textbooks might be a different chapter, but in OpenStax textbook, this is chapter 7. So let's get started. We are going to mainly talk about lots of different identities, as you see over here, and then at the end we're going to solve trigonometric equations. Of course, we start with simple identities and two simple equations, and then we continue with other identities and equations that require a little bit more work, and modeling with trigonometric equations, which is about harmonic motion and damped harmonic motion. Okay, these are very useful, and you can read in the text and you see that there are many applications in the describing the transmission of images, light, and sound. Sinusoidal graphs can model music playing on a phone, radio, computer. So lots of different applications. So let's just start with the identities that we already learned. This is Pythagorean identity, and we said that if we divide everything by cosine squared, we end up with this one. So this is the second trigonometric identity called Pythagorean identity. And then if you divide everything by sine squared, you get this. And this is the third one. So we can use them as we need them in solving equations or simplifying trigonometric expressions. As you see, that's something about trigonometry that you should know, and that is expressions that are exactly equal, they look very different. Okay? So when we simplify expressions in trigonometric expressions like this, for example, when we divide by cosine squared, we assume that cosine squared is not zero. So when you simplify a trig expression, the domain actually may change. So we have to take that into account. The domain might change. But in this case, since tangent squared here, we know that has cosine squared under it, and we didn't cancel anything really. So we don't have to worry about it in this case. So, but there are situations when we use some algebra to simplify things, we divide by things and cancel, then the domain changes. In this case, it doesn't, because the restrictions are still there. You see, tangent has that restriction, that denominator cannot be zero. Secant still have that restriction, right? All right, so, and there are other identities. We talked about even and odd identities, and that is basically which trig functions are odd and which ones are even. And we know that cosine and its reciprocal are even. That means they are symmetric with respect to y-axis. Then also it means that cosine of negative x equals to cosine x. Now, so cosine and secant are even, and the rest of them are odd. So sine is odd because, as you see the graph, you know it's symmetric with respect to the origin. And also you know that sine of negative x equals to negative sine x, and that's the definition of an odd function. If that's the case, then the function obviously is odd. So sine and the reciprocal of sine, cosecant, tangent, and cotangent are odd. cosine and secant are even, okay? And you can see why, because tangent and cotangent have to do with sine and cosine. And when you divide, tangent is sine over cosine. So tangent negative x is sine negative x over cosine negative x. But we know sine negative x is negative sine x. So, and cosine negative x is just cosine x. So we end up with negative tangent x, which proves that tangent is an odd function. Okay? These are reciprocal identities, and again, we talked about these already. We even used them a few times in other videos and chapters. So sine is 1 over cosecant, so cosecant is 1 over sine. See, they are reciprocal of each other, right? Cosine is 1 over secant, so secant is 1 over cosine. Tangent is 1 over cotangent, cotangent is 1 over tangent. And quotient identities are tangent and cotangent, and we know that already. These are by, definitions, we get these. The 3 definitions, remember? Either one you use, you can get these. So either you use the first definition, where we use the angle here, and then we call this A, B, C, or second definition, when you put the angle in a standard position and put a point on the terminal side, we call this R, call this X and Y, and then use them to define 6 ratios. Or the third definition, which is unit circle, and we say that the coordinates of this point is cosine theta and sine theta. And theta is this angle here. All right, either one you use, you see that these reciprocal identities actually work, right? With the way that we define them. All right, so now how do we verify identities? If you're given an identity, how do we verify it? Now, the ones that are in the table of identities, we don't have to verify them. We don't have to verify that cotangent is, 1 over tangent. So these are given, so we don't have to prove them. But if somebody gives you something like this, it says, what is sine? If sine theta times, cotangent theta equals to, let's say cotangent is what? Cosine over sine, so equals to cosine, theta, something like that. Now, in order for this to be true, we have to write cotangent as cosine over sine, right? And this sine cancels sine, and we get cosine. That's how we can verify it. Now, so we can start from the side that is more complex. Why? Because it's easier to simplify than to build. So if you want to build cosine to look like sine times cotangent, is harder than just start with sine cosine and simplify it into cosine, right? And again, remember we talked about that. If you write something in trigonometry equals another expression, these two expressions are equal, but you got to watch for the domain. If you think of this as a function and that as a function, these are not actually exactly the same domain, because when you divide by sine here, sine cannot be 0, right? So that means when you write this as cosine theta, well, how do you know that sine cannot be 0? Well, we don't, because it doesn't look like it. So when we simplify, we have to realize that where this comes from, right? And take that into account. But for now, for our purpose here to verify identities, we don't care about that. So we start with the more complex side, and then we look for this structure. So this is in the background in our mind. So we simplify this looking to get cosine out of it, right? And if possible, we do it. If not possible, if it's too complicated, maybe we can take everything and write them in terms of cosine and sine, like I did here. And then cancel what we can cancel and see if we can get the other side. So let's practice with this a little bit. And that's this section here. And then I do two simple equations. So here's the first example. Verify that tangent equals to sine times secant. So we start with a more complicated side, right? And then we have this in mind. We're going to try to make this look like tangent. So we can write secant as 1 over cosine. And then right away we see the structure is tangent actually, because sine over cosine is tangent. And since everything we do here, if everything we do is reversible, then we don't have to go from right to left and from left to right to prove this. We could just do it in one direction, assuming that everything we do here is reversible. Now there are some operations that are not reversible. Like if you take a square root of both sides, right? Then, or do some other operations that is not reversible, like, things that they're not one-to-one, then that's a different story, right? So so let's look at, so in this section, we assume that everything we do is reversible unless it is stated and unless it is involved some operation that is not reversible. Otherwise, we just assume it's reversible. So we can only go, we only need to go from one side to the other. Right to left or left to right. Okay, here's the second one. Verify secant over 1 minus tangent equals to that. Now, so we start with, this side has more stuff in it. So denominator has tangent, numerator has secant. So we can start with this and then write everything in terms of sine and cosine. So secant is 1 over cosine. Tangent is sine over cosine. And to simplify this, we can multiply by cosine over cosine, which is 1, right? So if I multiply by cosine in the numerator and by cosine in the denominator, I'm going to end up with this, right? See that? So cosine times 1 over cosine is 1. Cosine times 1 is cosine, and cosine times this fraction, the cosines get canceled. So we get sine minus sine. So we see we got the right-hand side. So we verified that this is actually true. So it's like a game of, it's like a puzzle. You have a bunch of formulas, you want to use them to make one side equal to the other side. It's important to know, to have some skill in simplifying expressions, because when we use trigonometry, we need it. So here's another one. We want to make left side equal to the right side. Start with the left side, and when we see that this is sine minus x, we can write it as minus sine x. And right here, see, start from here and write sine minus x as negative sine x. Now this looks like, in algebra, we have a plus b times a minus b is a squared minus b squared. We call it difference of two squares. So sine squared and plus cosine squared, we know is 1. So we use these two pieces of information here, and we assume that this is a plus b and a minus b. So the answer is a squared. If you think of this as a, and this is b, now a and b, right? B is the number goes after the minus, so b is sine x, not negative sine x. And then b is the number that goes after plus sine, which is b, which is sine x. So a squared minus sine squared, 1 squared minus sine squared is cosine squared. How do we know that? Because of the Pythagorean identity. Right? If you move the sine squared to this side, cosine squared is 1 minus sine squared. So we get 1 minus sine squared, which is cosine squared, and that's the right-hand side. So we verified that. Right? Here is another one. It says rewrite strictly in terms of sine. So we want this to look like just in terms of sine. Well, we just, tangent is sine over cosine, and secant is 1 over cosine, right? So if we write 2 times sine over cosine, and then times 1 over cosine, we end up with 2 times sine over cosine squared. Now cosine squared is 1 minus sine squared, again we know from here. So this is strictly in terms of sine. There is no other ratio in it, right? So in many cases it's convenient to write a trigonometric expression in terms of one trig function only, if there are many of them. That's very convenient. In solving equations is convenient, and in applying models is convenient here. To create models, it's convenient to have one function. And in computation, it's convenient to have one function. So computer can deal with it. Here's another one. Again, we have both sides kind of complex, but this side has more stuff in it. So we can see if we can make this look like that. And again, there are many different paths to go. Some of them are dead end. So by practice, you're going to see how to do this. So you see, the numerator looks like difference of 2 squared. If you put a 2 over the 1, it doesn't change anything, right? So that's sine x minus 1 times sine x plus 1, right? It's like a squared minus b squared, right? And so that's a minus 1, a minus b times a plus b. Now, denominator, if you factor the tangent out, you end up with sine x minus 1, and they get cancelled, right? So the answer is sine x plus 1 over tangent x. Okay, again, we are losing one restriction here when you write it this way, and that is that sine x cannot be 1. Because if sine x is 1, the denominator is 0, and we can't divide by that. We cannot cancel these if there are zeros, right? So, as I said, we are not going to care about that now, but you have to take that into account when you deal with this. This is not exactly the same as this. The domains are different, right? All right. Here is another one. It says, write an algebraic expression for this. Well, algebraic expression means something that it is not algebraic because it involves cosine x. Algebraic expressions are the ones you can use variables, operations, right? And, raising to power. These operations and variables and numbers, to what? To create them. You can't do that with trig functions. You cannot represent sine x as some, algebraic expression of x easily, right? So these are not algebraic functions. They're called transcendental function. Trigonometric functions and exponential functions and logarithmic functions are not algebraic. So what we want is just an algebraic expression that kind of looks like this. So we can write, think of cosine x to be m. So this looks like am squared plus bm plus c. For what? For m equal to cosine, right? And then why do we do this? Because in case we want to solve an equation like this, right, how do we solve that? We can't isolate cosine. So what we have to do is convert it to an algebraic expression like this and find out what m is going to equal to. Then we know m has to be cosine. Then we can go in that path and find out what cosine is. All right, so we're not solving an equation here. We're just writing this in terms of an algebraic expression. Here's another one in terms of algebraic expression. This looks like difference of two squares. This looks like a quadratic expression, right? That's quadratic. So we call these quadratic in kind of quadratic form. They have a form of quadratic, so we can do this, think of cosine as m or some other variable, doesn't matter, and then convert it to an algebraic expression. We can do the same here. We just have to think of this as something is squared and this as something is squared, which we can do by thinking of 2 cosine x be a and then b be 1. So this can be written as 2 cosine, well, I wrote it here. So 2 cosine x is squared minus 1 squared. 2 cosine x is a and 1 is b, right? So it can be written this way as an algebraic expression, right? All right, so let me solve 2 simple equations here, and then I'm gonna end this video and we're gonna continue with identities later. So suppose we want to solve this equation sine x equals to 0.8, and we want to do it in degrees and we do it in radian too. So in order to solve this, we have to isolate x. So how do I isolate x in this expression? Well, in algebra, if we have 3x equals to 0.8, we just divide both sides by 3. Well, we can't do that here because, you know why? If you divide by that, what does that say? It's a sin. Don't do that. You get in trouble. So we don't want to do that. You don't divide by sin. That doesn't make any sense, right? So what do we have to do to get rid of this? We have to use the inverse. So we have to take sine inverse of both sides, like this. Now this side is x. Now that side, remember sine inverse, to get sine inverse, we put restrictions on sine. So remember the answer, the question here is, what is the angle in negative pi to pi over 2, from negative pi over 2 to pi over 2, to have a sine of 0.8, okay? So we're looking, if you put in a calculator is going to look in, this area here to find an angle whose sine is 0.8, right? So here's unit circle. Calculator is going to look for an angle that has that sine, which is about 0.8. Let's say over there. See? So calculator is going to give you this angle. Now, that's not the only angle that has sine 0.8. That's how sine inverse works, right? But in this equation, we are interested in all values of x that gives you sine of it 0.8. So sine inverse gives us one value, and we use that one value to find all of them. Okay, you can use calculator because we don't know, we didn't memorize an angle whose sine is 0.8, so we use a calculator. So calculator gives us that, which is this right here, which is 53.13 degrees, right? So that's 53.13, right? So it's an irrational number, so calculator gives you many decimal places. You can round it, but that's the answer in negative 90 to 90. That's what the calculator gives you. Now, we put it over here, we say, okay, what other angle in 2 pi radian has the same sine? Well, this one. And what is that? Well, this angle is basically 180 minus what? Minus this part, which is the angle the calculator just found. So you're in degree, I'm in degree mode here. I do sine inverse of 0.8, I get 53 point something. And I'm going to use every decimal place in the calculator by finding this one by subtracting this answer from 180. So 126.86 is the other one. So we got two angles that have sine 0.8, but those are not the only two, because we can go around once and get here. We can go around twice and get here. So just to get to this angle, we can do 53.1 degrees plus 360K, right? That means for whatever K is, we can find another angle that has the same sign, right? So for example, if K is 1, we go around once and we get here. If K is 2, we go around twice and we get here. This is also has the same sign. Now we could also go do negative angles. If K is -1, that would be a negative 300 something, which is that. And also if K is -2, we can go around once in the negative direction and come over here, right? So it looks like we have infinite number of answers just over here. What about here? Well, that's a different story, because you can never get from here to here if you just add 360 or subtract 360, right? So we have to consider another value, another equation for x, which is this angle, which is 126.8 or 0.9 plus 360K. All right, now these give all solutions for that equation, all solutions. Now, in application, you don't want to round for people who want to use this. So you could write it this way. You can write it as x equals to sine inverse of 0.8, right? So that, and then plus what? Plus 360K for this one. So instead of actually figuring out what that is and round it, we just put it this way so people who want to use this decide how many decimal places they want to use. And for this one, we can write x equals to 180 minus sine inverse of 0.8, and then plus what? 360K. So now we get a bunch of answers from that one, right? So this way, people who want to use this decide how many decimal places they want to use. Okay? So that's how we solve trig equations if we are looking for all the solutions for the equation, right? And I'm going to give you a note here that when you use a calculator, remember, calculator only gives you one answer. And that's good because of that one answer, we were able to find that one and all of them, right? So it's a powerful tool right there. All right, so once we have one answer, then we go in one turn and find all the answers in one turn. And then we write them down, then we add 360K to them, right? Okay, so I'm going to show you the answer typed right here. You can stop the video and look at this one more time yourself, but I explained all this already. So this is if the values we are interested in, to report are in degrees. What if you want it in radian? Well, if you want it in radian, then you use radian, right? Here we go. Well, looks like if you want it in radian, then you're going to do, let me do it here. So all you have to do is this answer that the calculator gives you, it would be, let me do it. So thing for the calculator. Okay, here you go. So if you want to do it in radian, you put your calculator in radian, and then you do what is sine inverse of 0.8. It would be 0.92 something. So here you would write x equals to 0.93, let's say, plus 2 pi k instead of 360k. And what about this one? Well, this one you have to take pi and subtract the answer from it. Then it would be what? It would be, whoops. It would be, let's see, x equals to 2.21 radian plus 2 pi k. 2 pi k, right? Now, if you want to write it in general with the sine inverse, the only difference is that instead of 360 here, you put 2 pi, and instead of 180 here, you put pi, right? So that's how you do it in radian. All right, let me do one more, and this is on cosine instead of sine. So we have given that cosine equals to 1/2, and we want to find all values that satisfy this. So we write, again, we do the same thing. We take cosine inverse of both sides. Cosine inverse of cosine x equals to cosine inverse of 1/2. Then we use a calculator. We don't need a calculator really, but if you do it, you get the correct answer. We know it's 60 degrees. So for calculator, where does the calculator look for answers? Well, in this case, calculator looks over here because that's the restricted domain for cosine. So calculator says, okay, what is an angle here from 0 to 180 that has cosine 1/2? And that is 60 degrees. So that the calculator gives us. Now we go around and say, okay, in one turn, where is another angle that has that? This angle that has that cosine. And we know this angle would be 2 pi, which is 360, minus 60, so it's 300, right? And in radian, of course, you know, it's 5 pi over 3. And 60 in radian is pi over 3. Okay, now, so what we do again, we write what? X equals to 60 plus 360k, and then x equals to 300 plus 360k. These give all the solutions for what? For this equation. If you want it in radian, you write x equals to pi over 3 plus 2k pi, or 2 pi k, and x equals to 5 pi over 3, 5 times 60, 300, plus 2 pi k. And these give all the solutions in radian, and these give all the solutions in degrees. And you don't have to write it in terms of cosine inverse because we have an exact answer for cosine inverse. Right? So again, I'm going to give you the answer, typed answer, and you're going to stop the video and take a look at it, see if it makes sense. So this is in radian, right? You can write it in degree as well if you want to. Okay, so I'm going to end this video, and I'm going to do this in the next video. So I am going to see you in the next video. Okay, let me come back here and say bye to you, and take care of yourself. See you in the next video.